In video 1, we're going to look at indirect measurement using similar triangles. So the idea behind similar triangles is real basic. The idea is that if we have a given triangle that has angles alpha, beta, and gamma, my gammas always suck. And if we have any other triangle that has exactly those same angle measurements, then we say that those triangles are similar. Triangle A and triangle B have matching angle measurements, therefore they are similar triangles. So in this particular case I used GeoGebra and I constructed 3 triangles, each of which has the same angle measurements as does my original triangle. And so the idea is this. The idea is that for one triangle to be similar to another, in other words, for one triangle to have the same angle measurements as another, it just needs to be a scaled up or scaled down version of the original triangle. In other words, if this side here has length A, this side the height, in fact let's use this is the base, and this is the height of the original triangle, that there's going to be some scalar k, some positive real number, so a real number that is positive, there's going to be some scalar k, so that this big triangle, each corresponding length, is just going to be k times the original length, k times the height, k times the base. This length here, let's call it L. This is actually a right triangle, but we'll pretend that it's not. So if this is L, then the length, the corresponding length over here has to be k times L. So sides attached to corresponding angles will just be scalar multiples of each other. So you either scale it up if k is bigger than 1, you're making a larger triangle. If k equals 1, then you've created actually a congruent triangle, which is a special type of similarity. And if k is a number between 0 and 1, then you will have created a triangle that is a reduced scale copy of the original. So in this particular example, I actually constructed this larger triangle so that it's twice the size of this one. So that means if we have length measures L, H, and B, the length measures on this have to be twice L, twice H, and twice B. And I actually constructed this triangle so that it was identically sized with the original one. So this has to have length 1 times L, 1 times H, 1 times B. And this guy was constructed to be exactly half the size of the original. So his lengths are going to be a height of 1/2 the original height, 1/2 the original length, and 1/2 the original base. And the good thing about, or the nifty thing about similar triangles is if you take ratios of corresponding sides, you get an invariant, you get a constant. So for example, if I take the ratio of the height of the original to the base of the original, if I take that ratio, height divided by base length, I'm going to discover that any triangle that is similar to that is going to have the same ratio, h over b. So for example, this larger triangle, his height is twice h. So if I take the ratio twice h to his base, which is twice b, what I see is that the 2's are going to cancel because 2 divided by 2 is 1, and I'm going to wind up with 1 times h over b is just h over b. And that's going to work itself out for each of the 3 similar triangles that I constructed. The scalar reduces to a 1 by division. So if we take 1/2 of h over 1/2 of b, the halves will cancel, the 1's will cancel, you'll get 1 times h over b. Hey, we get this invariant or constant ratio. In fact, for any positive real number k, k times h divided by k times b is just going to be h over b. So we can use this idea that ratios constructed using the sides of similar triangles, side ratios are constant, and we can, anytime we have something in math that's a constant or invariant, we can then use it to solve problems. So here's a common application of similar triangles. So to estimate the height of a tree, myself, Richard, who is 6 feet tall, I measured the length of my shadow. I went outside just a little bit ago. I measured my shadow length. There I am doing it, and my shadow was 48 inches long. I then measured the shadow length of one of the maple trees in my yard, and I got the shadow length at 269 inches. So the idea is, if I'm standing in my yard, so here's me, here's Richard, and I cast a shadow, and that shadow has a length of 48 inches. And my height is 6 feet, which is equivalent to 72 inches. So Richard is 72 inches high. I can then construct a triangle from those two measurements, the height measurement and the width measurement. And if I assume that I stand perpendicular to the ground, so I'm not leaning, I'll have about a 90-degree angle here. I'll be roughly perpendicular to the ground. And if I have a tree in my yard that has some height that I don't know, but I can measure his shadow at 269, and I assume that the tree is roughly perpendicular to the ground, I actually wind up with two similar triangles because the sun is so far away and I am so close temporally to the tree. The angle at which the sun rays are hitting the top of the tree and the angle at which the sun rays are hitting the top of my head are going to be the same. So I have a triangle with the angle alpha, which is the angle that the sun ray is making with the top of the tree. The angle alpha, the angle the sun ray makes with the top of my head, those two angles are the same. So if I have two 90-degree angles and two alpha degree angles, I know that these two angles also must be the same, which means I have two similar triangles. The moment I know that I have two similar triangles, I know that ratios of side lengths are constant or invariant. So I know that h over 269, the ratio of the height of the tree to the length of its shadow, is going to be exactly the same as the ratio of my height to the length of my shadow. So again, I match things up based on the angles that I'm attached to. So 48 is attached to the angle beta. It's in the denominator. The 269 is attached to the angle beta. He's sitting here in the denominator. I set up the side ratios from the two triangles, and then I just solve it for h. Multiply both sides by 269. We get 72 times 269 over 48. So the height is going to be, and the calculator says that's 403.5 inches, or I could convert that to feet. 403.5 inches times 1 foot per 12 inches, so the inches go away, and that's going to give me 33.625 feet. These measurements, 48 inches and 269 inches, are probably slightly off, so carrying something out to 3 decimal places is probably a little bit absurd to do, so we'll just say, hey, the tree is about 34 feet high, which is actually 4 feet higher than I was estimating it to be. So that was interesting. So here's another application of similar triangles. Well, and again, so if I just slip back a slide, the title of this was Indirect Measurement and Similar Triangles. And the idea is we'll have things like this, the height of a tree, that unless we have a really tall ladder, we can't measure. So it's an indirect measurement. It's measuring something without being able to actually take a ruler and measure it. So here's another type of indirect measurement. Suppose you want to estimate the width of a river. So to do this, what we can do is side in at a particular angle across to the other side. side in at a particular angle across to the other side. Estimate where the line would be drawn that would bring you from this side to this side so that you hit the opposite side at a 90 degree angle. And then draw the line from yourself down to the river, make it hit also at a 90 degree angle, and then you're going to have some distance between the two. And the line across your line of sight going across here, you can't actually draw the line, but you could draw it on paper. It's going to have some intersection. And what we know is that vertical angles are the same, which means whatever your sight angle beta is right here, because this is alpha 90 beta, this is alpha 90, that's going to force this to be beta. It tells us that we have two similar triangles. So if I want to know the width of the river, it's simply going to be the distance from here to here divided by the measurable distance from here to here, 61 meters, is going to equal the distance from here to here, 16.1, so corresponding lengths, divided by the distance from here to here, 25 meters. And then we just multiply both sides by 61, divide it by 25. Calculator will spit out a number if we're lazy and don't want to do it by hand. It's giving me 39.284, and this is in meters. And again, round to the nearest meter. This is coming out of the online homework platform. This is an example of a problem in the online homework platform. And I think in this case, this is a reasonable way to round it to the nearest meter, because again, we're going to have some roughness in these estimates, so carrying it out to a bunch of decimal places probably doesn't make sense. It's about 39 meters.